All right, on the next page, and it's page 53 for me, but I think it's probably page like 56 or 57 for you, we are finding the absolute extrema of f on the closed interval from 0 to 5. So just like before, the first thing that we want to do is find the derivative so that we can find our critical values. Oops, I'm trying to make my pen more narrow so I can write smaller. All right, so in step 1, and you don't need to label these steps, I'm just labeling them for ease of understanding the steps. So the first thing we want to do is find f prime. And I'm going to have to use the quotient rule taking this derivative. So low d high gives me e to the x times -1 minus high. I have to put this in parentheses because it is two terms. D low, so times the derivative of our denominator, all of that over low e to the x squared. And remember, you could write that as e to the 2x using our properties of powers from algebra. And typically, it helps to factor when we can our derivative. So since both terms in the numerator contain e to the x, I'm going to factor out a GCF of e to the x, and I'm left with -1 minus, and until I distribute that, I need 1 minus x in parentheses. And that's still over e to the x squared, which I'm going to write as e to the x times e to the x, because we can now divide out a factor, a common factor of e to the x from the numerator and the denominator. So in my last step of the derivative, I'm going to distribute the negative in the middle. So I get -1 minus 1 plus x, because that negative applies to both of those terms, over e to the x, which is the same as -2 plus x, or x minus 2 over e to the x. All right, so that's the form of the derivative I'm going to work with. All right, so in step 2, we said we want to then find critical values. Because our derivative is rational, meaning that it's a fraction, it's an expression over an expression, I do need to consider the possibility that f prime is undefined. So when I find my critical values, I suppose I really always need to consider that. I'm looking for where f prime equals 0 or where f prime does not exist. Well, for f prime to not exist, I would have to have a 0 in my denominator. So if I set e to the x equal to 0, I should consider that, but remember, e to the x is always positive. We have that ordered pair at 0, 1, and to the left we have that horizontal asymptote, so e to the x is never 0. So you can just go ahead and strike through that. It just shows us that we're considering e to the x, but it never equals 0. So now I just want to consider x minus 2 equals 0, because if the numerator of my derivative is 0 and the denominator is not, then that's a place where f prime is 0. So when x equals 2, f prime, our derivative, is 0. So x equals 2 is the only critical value that we get. All right, so now we said we want to make a table. So not a number line, but a table of values. And in our table, we need to consider the endpoints of the interval, 0 and 5, and our critical value, 2. So again, in our table, we're including endpoints of the interval, 0 to 5, and our CV of 2. And again, I'm not plugging these numbers into the derivative because I'm going to find the actual function values here. So f of 0 is going to be 1 minus 0 over e to the power of 0. So I'm using the function. Well, 1 minus 0 is 1, e to the power of 0 is 1, so f of 0 is just 1 divided by 1. For f of 2, I have 1 minus 2 over e squared. and that is just -1 over e squared. And then lastly, for f of 5, I have 1 minus 5 over e to the 5th, and that is just -4 over e to the 5th. All right, it's easy in this problem to tell what our maximum value is because it's the only positive number. So at x equals 0, f will have a maximum value of 1. But it might be hard to tell what our minimum value is. So I say, why don't we get common denominators? So since we already have a denominator of e to the 5th, I could make f of 2, -1 over e squared, and you could put that negative out front. I just kept it in the numerator. I could get common denominators by multiplying by e cubed. So this is the same as saying -e cubed over e to the 5th. All right, so now I just need to know if e cubed is greater than or less than 4. Well, e, we know, is 2 and some change, and 2 cubed would be 8. So I know that e cubed is a number that is more than 8. So this is going to be a more negative number. So this is going to be our relative minimum value. All right, so for our very last step, we just need to answer the question. So we could say, step 4, answer the question. So we could say that f has a maximum value, and we could also say abs max, absolute maximum, of 1 at x equals 0. So again, the maximum value is the y value. The location is the x value. And I could say that f has a absolute and absolute minimum value of -1 over e squared, or you could say -e cubed over e to the 5th at x equals 2. All right, so that one's not too bad, but we really do just have to apply some number sense, and we do need to know the ballpark of what e is approximately. All right, this last example seems really straightforward at first, but we're going to find that there's actually something really tricky we got to be careful of. So in part A, we are just finding the average rate of change of g on the closed interval from -3 to 2. So I know that this is g of 2 minus g of -3 over 2 minus -3. Out to the side, though, I would encourage you to evaluate g of 2 and g of -3 not in line, but just out to the side. It makes it less likely for us to make mistakes there. So g of 2 is, oops, nope, not 4. 1 over 4. 1 over 2 squared is 1/4. Getting a little ahead of myself there. And g of -3, remember we always sub a negative in parentheses. I get 1/9. So this becomes 1/4 minus 1/9 over 2 minus -3, which is 2 plus 3, which is 5. So from here, it's up to you how you want to simplify this, but I think the easiest thing to do is to multiply the numerator and denominator by 36, because 36 is the least common multiple of 4 and 9. So by multiplying by 36 on top and bottom, and I would want to, if I'm using an equal sign here, I would have to show that I'm multiplying by 36 in both places, since we know 36 over 36 is 1. So I'm really just multiplying this expression by 1. When I distribute 36 to both terms, I get 1/4 of 36, or 36 divided by 4, which is 9, minus 1/9 of 36, which is 4. And I'm going to leave my denominator as 5 times 36, because sometimes, like in this case, I can cancel out my 5s. So I can, by cancel out, I mean divide the top and bottom by 5. So it helps us to not do that multiplication until the end, in this case, so I don't have to divide back out a 5 after I've already multiplied 36 by 5. All right, so we get the average rate of change is 1 over 36. And again, we modeled showing our work, so we're always looking to see this thing we call the difference quotient. It's a quotient with a difference in the numerator and hopefully the denominator, but as long as there's the difference in the numerator, you could have written 2 plus 3 in the denominator. That would also be correct. And then again, be careful with the equal sign. I can use the equal sign here because I multiplied the top and bottom by 36. So I did not change the value of my expression since 36 over 36 is 1. So now in part B, must there be a value C on the closed interval from -3 to 2 such that G prime of C is 1 over 36? And so we know this is the mean value theorem that would guarantee this. I can guarantee a value of my derivative based on the average rate of change of my function. And I know that my function has an average rate of change of 1 over 36. So it's tempting to say yes. However, the hypothesis of the mean value theorem is that the function must be continuous on the closed interval and differentiable on the open interval from -3 to 2. And look at what happens to G at 0 though. If I were to consider G of 0, or if I just consider setting my denominator equal to 0, I would find that when x is 0, G of 0 does not exist. So we don't necessarily have to show all this work, but what we can say here is because G is not continuous on the interval -3 to 2, the mean value theorem cannot be applied. All right, so it's possible. So we can't say there must not be, but it's possible that there is a value of the derivative that's 1 over 36 on that interval, but the mean value theorem can't guarantee it. And for now, I think that this would be an acceptable answer for that question. All right, in part C, we're finding the absolute extrema of G. So again, we want to consider our critical values as well as -3 and 2. And so we already kind of know something funky is going to happen at 0. So if I take my derivative, in fact, I'm going to rewrite G. You can use the quotient rule if you want, or I could think of G of x as just x to the -2 power, so that when I take the derivative, I can just use the power rule, and that becomes -2 over x cubed. And in this case, since the numerator is just one term, just 2, you could put the negative with the 2 or keep it out front. The way I just wrote it, it is clearly out front. It's not in the fraction bar. So this is why it's important when we're finding critical values to remember that critical values are where G prime equals 0 or where G prime does not exist. Because based on the nature of our derivative, G prime's never 0 because it's a rational function and the numerator is either 2 or -2, depending on where you stick the negative. But if the numerator is not 0, G prime's never 0. Or if it doesn't have an x value, like if x isn't an expression in the numerator, I'm not going to get a 0 there. However, G prime would be undefined if x cubed equals 0. So if I take the cube root of both sides, I know that's where x equals 0. So I really get the solution x equals 0 with the multiplicity of 3, if you remember that, meaning that there are 3 solutions, but they're all 0. All right, so now we want to make our table. We already know something fishy is happening at the 0, and that's what's going to make this problem harder than it might seem at first. So in my table, I want to include x and g of x. So again, the function, not the derivative of the function, but actually the function g. So I already know I'm including my endpoints of my interval as well as my critical value, and we already found these values in part A. So we know g of -3 is 1/9, and g of 2 is 1/4, and g of 0 is undefined. So we could either write D and E for does not exist, or undefined, or non-existent. All of those things are synonymous. D and E is just short and easy to write. But here's the thing. We need to know more about what is happening at the 0, because we actually don't yet have enough information to answer whether we have an absolute min or max, because think about the function g. When we plug in 0, we get 1/0 squared, and that tells us that the function g has a vertical asymptote at x equals 0, because we get a number over 0. So we actually need to explore that a little bit more. So let's do so with limits. Uh-oh. All right, sometimes when my computer's plugged in and I'm recording, it like overheats. So I hope it didn't cut out on you. So the limit of g of x as x approaches 0 from the left. And I'm going to rewrite g of x right here since I'm zoomed in. We said g of x is 1/x squared. Well, as I plug in a teensy tiny negative number, because I already know I'm getting 1/0, but if my denominator is a tiny negative number, I'm still going to get a positive tiny number on bottom because I am squaring whatever is in my denominator. So a tiny negative squared is a tiny positive. So this tells me that g is approaching positive infinity as I approach 0 from the left. And then as I consider 0 from the right, well, I'm still going to get positive infinity, because if I plug in a small number and square it into g, I get a tiny denominator that's positive. So g is also approaching positive infinity as we look at 0 from the right. So that tells us that the function g has a vertical asymptote at 0, and what we know about the function, even if we don't know what it looks like, although in Algebra 2 we graph rational expressions, the function is approaching infinity in both places. So if you want, you could also look at it in Desmos. This is the graph of g of x is 1/x squared. I just plugged that into Desmos, and I could see that vertical asymptote there. So here's why that's important. This function has no absolute maximum. So we need to know that, or we need to know to check that, because one of our critical values was undefined. So I do have a minimum value, which is 1/9 on the interval, and that occurs at -3. So again, if I look at my Desmos graph, we were looking at this from -3 to +2. So I'm looking at the function from -3 to +2, and the minimum value is 1/9, which occurs right here. That would be the y value of that function. But as I can see, there's no absolute max, because at 0, both sides of this function are approaching infinity. They're getting higher and higher forever. So I need to consider that when I answer the question. So we could say that on the interval from -3 to 2, the closed interval, g has an absolute minimum value, not a max, of 1/9, so it's the y value that's the minimum, at x equals -3. But we could say that g does not attain an absolute minimum value on the interval from -3 to 2. And so lastly, I want to go back to that very first part of our notes, going back to the extreme value theorem. We said that if a function's continuous on the closed interval, from a to b, so some specific x values a and b, then that function attains both a max and a minimum on the interval. So it's the extreme value theorem that helps us understand that last example, how it could attain a minimum value but not a maximum. Because g was not continuous from -3 to 2, well, it turns out there is a minimum value, but there's not a maximum value there.